Hello, this is Bruce Nielsen. Today we're going to talk about cosine similarity, which is an important concept when dealing with semantic search, which is an important concept when dealing with retrieval augmented generation with large language models. So here we have cosine similarity as defined by Wikipedia. Does that make your head hurt? It does me too. Don't worry, I will explain it in detail. So let's start with a sentence. This video presentation sucks. And we're going to compare that to this sentence. This video presentation is awesome. So what we're going to do is we're going to create what's called a bag of words. So this is a very simplified way in which you could do cosine similarity. It would be way too simple to be used in real life, but it's much easier for a human to understand if I do it this way. So we're going to use a bag of words. We're not going to worry. What bag of words means is that we're not going to worry about the order of the words. We're just going to take the words and throw them into a bag. So in this case, we have each of the words. This video presentation is sucks awesome. So that's the total number of words across both sentences that we're going to be using to be able to do our cosine similarity. So what you then need to do is you need to take each sentence and you're going to simply assign a 1 if the word in the bag of words exists in the sentence and a 0 if it does not. So just so that you can see how this works, here's the different words, and you can see that I am assigning them by position and that I'm assigning a 1 if the word exists in that sentence and a 0 if it doesn't. So to explain this, it's probably easier if we start with a very simple example. Imagine you have a vector and you're simply going to measure the distance between the angles in the vector in a two-dimensional vector. So we have a 45-degree angle and we have a 75-degree angle. How might we measure the similarity between these two lines using only the degree in this case? Well, we might start with 75 degrees minus 45 degrees. That's 30 degrees. So there's a 30-degree difference between this line and that line. So we're going to take a cosine of that. Cosine with 30 degrees. I'm using degrees here, not rands. And we end up with 0.866 0.87 essentially. Now imagine instead we had 100 degrees versus 45 degrees. How would that work differently? Well, you'd have 100 minus 45, that's 55 degrees. You'd get a cosine of 55 degrees, which is 0.573. So what you want to do here is think of these as being like percentages, a percent of similarity. So in this case, we might think of the 30-degree angle difference as an 87% similarity, and the 55-degree angle difference as a 57% similarity. Now I'm cheating to be able to get that result because there's actually 360 degrees to play with, and I'm doing my math as if there was only 180 degrees. Now, why am I doing that? The reason why is because you can't actually have a negative word count. You might have negatives in other types of things, but in terms of words, you can't. Therefore, the cosine works out to be a percentage of similarity, but that wouldn't necessarily be the case with any type of vector you did. So let's actually talk about how this actually would work in real life. So I'm going to use code here that uses NumPy. NumPy is a popular Python library to work with arrays. And so we're going to do a cosine similarity using code from NumPy. So essentially we take the dot product of x and y. We're going to then take the magnitude, so the norm of x and the norm of y. And then you're going to divide the dot product by the product of the norms, and that is the cosine similarity. Now, could you do this without using NumPy? Absolutely. For some people, this might look a little easier to understand. For me, it looks really kind of complicated, so I kind of prefer the NumPy version. I won't go into all the details here. Well, I will actually go into all the details on the next slide, is what I mean to say. But in this case, it actually works it out in Python code, and then you get this cosine similarity this way. All right, so let's try to understand this formula now. So here's the Wikipedia formula again. So dot product, we take the dot of x and y, and then we're going to take the x magnitude, which was the norm of x, and the y magnitude, which is the norm of y. And then we're going to get the cosine similarity by taking the dot product dividing it by the product of the magnitudes. So how does this actually map to the formula here? Well, there you can see the dot product, and it is pointing to the top product right there. And then these two together, they represent the denominator there. And then this last one is the divisor, is the division symbol, basically. And then that therefore gives you the cosine similarity. So you can see this isn't actually very difficult. It's just simple high school level math. All right, so let's actually calculate this out as I promised, one at a time, just so you can see how it actually works. So here's our two sentences, our bag of words, ones and zeros, depending whether the word exists. So the dot product, you would take, now recall from your high school math, if you took this far in high school math, that when you're doing matrix multiplication, you're going to be comparing rows and columns, and to get a dot product, you're going to be multiplying them together. So we're going to do 1 times 1 plus 1 times 1 plus 1 times 1 plus 0 times 1, etc. It's going to end up adding up to 3. Just as a visual to help you understand what it is I just did, I basically went like this. I multiplied each of the columns versus, or the rows versus the columns, and then you add them all together. Then we need to find the magnitude. So the way you would do that is you would square each of the numbers, and then you'd add them up, and then you take the square root of the result. Recall that that is actually the way you would find the distance between 2 points in a 2D space. It's just in this case, we're generalizing to a hyperdimensional space beyond two dimensions. So basically, it's just the distance formula. So square everything, add them up, take the square root. That's the magnitude. So finally, you take the dot product, you divide by the product of the two magnitudes, and you get a 0.6696, basically 0.67, or 67% similarity. Now, to be honest, this isn't a great measure. So this was just done to make it simple so that I could explain it to a human audience. Since we're only looking at whether a word exists or not, it's not really going to give us a great result. And as you can see in this case, I've got literally two opposite sentences, and they're seen as 67% similar because all I'm doing is looking at the words. How might we actually use cosine similarity to be able to figure out that these are actually opposites? Well, the way you would actually do this in real life is you would use a text embedder. So there are individual text embedders, or you can use a large language model. They all have to have some sort of text embedding. And what text embedding is that you take a sentence and you pass it through the embedder and it turns it into a vector. Now, a sophisticated embedder is not going to just look at which words exist. It's going to look at the relationship of the words, where they are in the sentence, their order. It's going to try to understand words that are similar. They will be in a similar spot within the vectors, that embedding space that it creates the vectors. So for example, if I'd said it was awesome or it was great, it's going to see those as similar, and it's going to see sucks and awesome as being in very different parts of the vector space. Therefore, it will know that they are opposites instead of similar. So by using a text embedder in real life, you can get a much more powerful result. Now, is this going to be sufficient so that we can actually just use this and then that's all we need? Well, no, of course not. This is one tool in the toolbox. It's probably the most important tool, at least for me, it's been the most important tool, but it's just one of several tools. And there's going to be a lot of different things that we're going to have to learn before we can actually make retrieval augmented generation work very well. But you can see, hopefully, how having cosine similarity would allow us to do a semantic search where we can actually take blocks of text. So for example, with my AI Karl Popper that I showed off, I take each paragraph in each of his books and I embed them. And then I'm going to do a cosine similarity between the user's query and between the text that exists in all his books. And when I get the result back, is it going to be exactly the answer to the user's question? In a lot of cases, yes, but in a lot of cases, it'll just be something that I will then have to use with other techniques to be able to kind of get to an answer that's going to be a good answer to the user's question. So really it all comes down to the embedder. If you got a good embedding software, it will take the text that is in your database. In my case with A.R. Karl Popper, that would be every single paragraph from all the books that he ever wrote. And it will embed those into a vector, and then it will take the user's query, embed that, and then it will do a cosine similarity against every single piece of text that Popper has. Now, you might be wondering how this could possibly actually work, to actually run a cosine similarity and run that function that I just showed you against every single piece of text in the entire works of Karl Popper or whatever your database is. There's a lot more tricks and techniques I'm going to have to show you before we're going to be done here, because obviously that would be too slow. So we will take a look at more about semantic similarity search and how to use it in real life in a retrieval augmented generation pipeline in future videos. Don't forget to like and subscribe, and we will see you next time.